Hi there folks, it's Mike here and welcome to your first day in the C programming language. In this series, I'm going to show you a bunch of small examples in the C programming language, and what I'd like you to do is follow along. You're likely not going to understand every single detail of the C programming language, and in fact that's not the purpose of this video. The purpose of this video rather is to just introduce you to the language, syntax, the features, and some of the basic things that you can do in C. The good thing is C itself is a relatively small programming language. So in fact, what I'm going to show you is, well, most of the language. And then I'll leave you at the end with a few of the more advanced topics that you can go on and think about or watch other future tutorial lessons. Anyways, with that said, let's go ahead and start our rapid dive into the C programming language. Again, you don't need to do everything or understand everything, but I would like you to at least try to follow along in the examples, try to complete them the best you can, and even play around a little bit. So let's go ahead and start having some fun. All right, so where we're going to start is just in a text editor. I'm going to go ahead and open a file called hello.c here. And the first C program I'm going to write is a hello world program. So in order to do so, we're going to need to start off by just creating the entry point into a C program. That's this main function here. Every program in C generally starts with this main function. So here is where code execution starts. And then line by line, each of these commands will be executed here. All right, so what are we going to do here? Well, we're going to want to print something off. So I'm going to need a library to print something off, and I'm going to bring in the stdio, which stands for standard, that's the abbreviation std here, and I for input and output. So input to the computer and output to the screen from here. So let's go ahead and use a function. I'm going to do puts, which stands for put in the S for string, hello world, which is sort of the classic first program that you write in most programming languages, a \n to indicate that we want a new line character to be printed out. I'll close the quotations and put a semicolon. Let's go ahead and save this program, which I've done below here by just hitting colon and then W in my text editor, and then I'm going to quit. And now if I look here, I'll have this hello.c program. And in fact, a lot of people may not be using a terminal to follow along, so it might be helpful to just see in the folder that I have, again, this hello.c program. So let's go ahead and take a look at that and see what happens with hello.c. Now, C itself is a compiled language. So that means that I need to take this source code, or this hello.c program, and compile it into machine language. And our computers understand the machine language and thus can execute that machine language with the given instructions that we've given it. In other words, to print out a string that says hello world. So let's go ahead and try that. Now, in order to do this, I'm going to need a tool called a compiler. That's called GCC. I'm going to feed it in this source file, and then in return, it's going to give me the machine code as output. So -o, that's a lowercase o for output, and my program name, which I'll usually abbreviate as prog, short for program. I'm going to hit enter, and if successful, you'll see I now have an executable program here. If you're executing or following along on a Linux system like I am, or on a terminal, you can then write /prog to execute the program. If you're on a Windows machine or so, you might get something with a .exe that you can execute. Okay. Let's go ahead and hit enter, and we'll see our program here, hello world. All right, so it really is as simple as that in the C programming language. Now, in the next segment, we'll go ahead and take a little bit of a closer look at C and what is going on in that simple hello world program. All right, recall that we have this hello.c program. And in fact, I don't care what application you're editing your source code in. It could be, as I'm going to open up, just a plain old text editor like this, where you're just writing each of the commands in. Or you could use something that's more popular these days, like Atom, Sublime, Visual Code, and so on. For me, I like using the tool Vim, which is a text editor that you can use on the terminal. And this will allow you to work anywhere. So that's what I'm going to be using in this tutorial, but don't feel overwhelmed to learn that tool. Now, let's go ahead anyways and open up our hello.c program and see what's going on here. Now, there's actually quite a bit going on in this first program. the good news is once you understand what's going on here, you're pretty much all set to go with all the other C programs that you write. And for this explanation, I'm going to go ahead and be ready to draw a little bit of just what's going on here. So let's go ahead and just look at this source code here. This is our hello.c program. And the very first thing we do, or the very first line of code we have, is we're including that standard IO library. And when I mean including a library, I literally mean somewhere going to a bookshelf. Here's my bookshelf with a bunch of books here. And one of them, let's say this one, is the standard IO library here. And we're asking in our C program to bring it in. That's essentially copying in all the different functions that we might want to use. So for example, this function puts, or puts for put a string here, is an example of a function that belongs to this standard IO library. So again, that gives us access. And then we have our entry point, which is a function itself. And I'm going to talk about functions a little bit and how they work in C, but basically it has a function name, some arguments. In this case, I haven't specified any, and a return type for the function. What are we returning? Some integer value. And that's what this part is at the bottom of our code. All right, and then of course, since we're entering our program, we're starting execution here at line 5, and then moving down in one line at a time executing our program until we return from this function, and then finally finish our program. So again, that's the body of our code in the main function here. And I'll just indicate that there's a bunch of code here. All right, now I also did talk about this other step of compilation. So I need to save this file, and usually you'll get some indication that it's been saved. And then what I'm going to do is pass this file into a tool called a compiler. That was a tool we saw called GCC. You might see some other ones like Clang, for instance, which I'll write out here. It's not pronounced C-lang, it's actually Clang. And basically what that does is it turns our source code here, after going through GCC, into a bunch of ones and zeros. And that's the machine language that our computer actually understands. And then our computer essentially takes this, also gluing in any library code. So there's a special step called the linker, which we'll eventually talk about at some point in a tutorial series. And then we get a executable file or a binary file here. And that's what we execute here with /prog on our Linux system. And then it prints out hello world. So as you can see, there's quite a bit going on here. And I think it's something that's going to be a little bit different than for folks who come from, say, Python or maybe JavaScript as your first programming language. So you might not be used to doing this step here, which I'm going to label as compilation. And that means that every time that we make a change to our source code, that's what's on the left here, that we have to recompile our software. So I'm always going to save this file, run it through GCC, and then test out the output. I call this the sort of save, compile, and run loop. So we'll want to remember to save, compile, and run over and over and over and over again. And that's going to be fine, and that's a good thing to do as you make small incremental changes in your C programs. All right, so with that said, let's go ahead and start getting ready for our next topic. All right, for this lesson, let's go ahead and return to the code here for a moment. And let's talk about variables. Now remember, when we're programming, our machines are actually going to need to store some data at some point. And in fact, let me go ahead and bring back our drawing board just so we can have a visual here of our machine executing here. And here's a little keyboard and a mouse. And we might want to store some data here. So let's say I have some variable here like x. And x somewhere in memory is going to store some value such as the number 42. And again, that's what we call a variable. And these variables allow us to programmatically store information. Now there is a certain type here int, as you might imagine, stands for integer, and that means that x can always hold integer values. So things like -1, 0, 7, 8, 1 million, etc. Those are the types of values that can be stored. And we call these primitive types, and they're built into the C language, so we don't really have to do anything with them. So let's just go ahead and see an example with the code here. So I'm going to get rid of our hello world, type in int x, and whenever we create a variable, it's best if we also assign it a value. That way we know what's stored in it. Now, if you're a mathematician, you're probably screaming here when you see this assignment, because we can actually reassign the value to something else later on in our program. But that's okay, that's how programming works. Again, variables are just boxes where we can store a specific type of data, like an integer number, 42, in this named symbol, x. All right, now our program at this point isn't very good though, so let's actually just print out that x value. So in order to do this, I'm going to teach you another print command here. And this one's called printf, for printing formatted text. And it starts off by saying a string, so x is, I end the quotations, and then the value that we want to print off. But in order to know where we want to place x in this string in printf, we use a format specifier, which I'll label %d, and there's specific ones for specific data types, such as x being an integer, so it uses %d, and it'll essentially substitute x into this position. So let's go ahead and run this. Now, I'm going to go ahead and do something with my terminal, a little trick where I can split the screen. That way you can see the code in one window here, while I compile in the other window. So let's go ahead and do that. Again, GCC, our compiler, the program that we've written, hello.c-o, and prog. And it compiled fine. I'll run it, and we can see our value here, x is 34. So great, we've successfully allocated some memory that is somewhere on our machine here. In the C programming language, we've created this variable x, stored a value, and we can change that value if we like, and then finally print it off. Now there's lots of other types of variables that we can work with, things like floating point values. So let's go ahead and create another one, float. I'm going to call this one pi, as it might be something familiar, and we can assign it some value here. And usually we put a prefix for some of these types here, like a float of f after it. So let's go ahead and do another print statement, and this time substituting in pi, a different format specifier because it's a different type, %f, and what we want to substitute into %f, which is pi. And let's go ahead and rerun this by recompiling it and rerunning, and we can see the appropriate output here. Now you'll notice that a floating value has several significant digits, so it added a few zeros here when I printed that off. And just to make things a little bit more concrete, let me go ahead and show you how I can comment out, that is, avoid these commands from being executed or compiled. And let's just go ahead and do the same thing, but with just one printf statement. So printf, x is %d, then I'll do an end line, and pi is, and I'll do %f for a floating point value, end line, comma, x comes first, then pi, and then a semicolon. And I'm going to extend this screen just a little bit so you can see everything on one line. Because I've made some changes, I'm going to make sure I save. My file has been written, recompile, rerun, and we'll see our output here. Now there's extra space here because it literally put in a space here, but I'll leave that for you to fix. All right, let's move on to our next topic. So something that can happen is if you want to store a lot of data, and we have to sort of think about how much data there is in the world. Well, there's a lot. There's, well, more than megabytes, then there's gigabytes, terabytes, petabytes, exabytes, and more. But let's just start with something small here. What if I want to store, say, 5 values? Well, we've learned how to use variables, and we can actually just create 5 variables. So I could have x1, and then I could have x2, x3, x4, and yet another x5, and we could store data like this one at a time. Now you could imagine though, if I have hundreds of thousands of variables, that this would get very, very tedious. And honestly, it's kind of a waste of space to store all of this here. So instead, what we have in C is a data structure built in, and that data structure is known as an array. Other programming languages, again, if you're coming from Python, don't really have a native array data type. So allow me to explain how this works. So again, let's try to store 5 integer values. So what are we going to do? Instead, what we're going to do is go int, and I'm going to abbreviate this as array, or that's the variable name, and then how much data we want to reserve, 5 here, between the brackets. And this gives me 5 consecutive locations in memory to store my data. So I'm just going to represent this as such, and I have my array here. So array with 5 elements in it. And in C, we index from 0. So the first element will be 1, 2, 3, and 4 as follows. Now let's actually populate this array with some data. And I'll go ahead and do that one at a time. So 0, and I'm just going to give a random number, 23. And whoops, a few too many random numbers. Let me just do one at a time here. Array 20 at 0 equals 23. Array 1 equals 0. And these can be any integer values. -7. Array 3 equals 45. And array 4 equals 76 here. So now I've successfully stored a bunch of values one after the other here. And again, I'll show 23, 23 here, 0, -7, 45, and 76. And an array is what we call a data structure. And it's a data structure because, well, we're storing data and we have it structured, one item after the other. And this is a nice way to collect all of our data in a contiguous block of memory. That's what this is here. Because remember, we're eventually storing this all in our memory. And this is getting to the point of where we're starting to think like a C programmer. We're thinking about these data structures like arrays and how things are stored in memory. That's one of the reasons to be learning C, by the way, because it makes us think about memory and some of these lower level concepts. And it's a great way to learn about how to optimize your code and write really, really efficient data structures. All right, so let's go ahead and print off these values here, and then we'll move on to the next lesson. Now I'm just going to print these one at a time like we did before. Array 0, and that value equals some integer value, an end line, and we'll do array 0 here. And repeat. And we need to update the indexes in each of our strings and the actual variable that we're substituting. Make that 2, 1. And let's go ahead and recompile and rerun this. And we can see our array printed out. And I'll make it just a little bit smaller so you can see everything on the screen here at once. All right, so now we know how to collect all of our data in a contiguous block. Now, some other notes about arrays is all of these values have to be integers. Because remember, we declared this array as a int array here. So they can't have floating point values or other types of values in them. They're all guaranteed to be integers. All right, in the next lesson, we'll look at a little bit of a more efficient way to print off some of these array values. All right, so previously we've looked at arrays, but typing out all these printf statements became a little bit tedious. In fact, initializing all these array values was also a little bit tedious. Now, it's always good to initialize our values, so it's nice that we initialize them to something. But let's go ahead and take care of printing out all these values. And we can use a programming construct known as a loop. So let me go ahead and demonstrate what we're going to learn here with a for loop. And a for loop allows us to do some condition over a period of time or a series of iterations. So let's just go ahead and look at an example and see how it's used, and then we'll formalize it a little bit. So what I want to do is just say for and I'm going to create a integer here, I equals 0. And while I is less than 5 because, well, we have 5 elements in our array that we want to loop through, I plus plus. Or I can just write I equals I plus 1. And what I want to do is printf the array, the iteration, that's I here, or the index in our array, and then print off what that value equals. That'll be our second integer here, and then an end line. So again, we'll have two different parameters here for our printf, the first being I, or the index into our array, and the second being the array at index I. And let's go ahead and compile, rerun, and we'll see that we get the same output. So we can see that this for loop made our code a lot more efficient. And it also expressed clearly what our intent is to do in the programming language. That is that we want to loop through all the elements in this array. So how does a for loop work? Well, we have the for statement, and then we have some initial statement here that we want, and that was setting I equal to 0. So this is essentially creating some variable that's going to exist within these curly braces here for this for loop. And then we have a semicolon. And then I say I less than 5, which is, in other words, just some conditional statement. So as long as that conditional statement is true, that is I less than 5, execute this code. And at the end of our code, we have some work that we can do here. And this work that we can do is just some expression that's being evaluated as soon as we hit this curly brace at the end. Then we're saying increment I equals I plus 1, or you can do what I previously did as a shortcut and just say I plus plus, which also just increments I by 1. So I'll go ahead and make that change, rerun, compile to show you that it does just the same thing. So that's an example of a for loop. We'll go ahead and look at some examples of while loops next. So in this example, let's go ahead and look at another type of loop in C known as a while loop. So we'll learn by example, while some condition is true. So I need to create some sort of integer here. And I'm just going to call this one countdown, set it equal to 10, and some condition. While countdown is greater than, let's say, 0, then let's go ahead and print out the countdown variable here. And I'll actually just put a %d here, and then the countdown variable, and then I will subtract or shrink from countdown. You can use minus minus or countdown equals countdown minus 1 here. So let's go ahead and see what this program does. Since I've made some changes, I need to recompile and rerun, and we can see the appropriated code here doing 10, 9, 8, and so on until we reach 1. Or that is rather, as long as countdown is positive, then this loop will continue executing. So just to break out the anatomy of a while loop, I have while, some condition, and then the associated curly braces and whatever my code is in between that will execute every iteration. Now there's also do while loops, which will flip the execution. That is, you'll have a do statement, curly brace, and then the while portion will evaluate the condition at the end. So it's guaranteed to run once. So you might see both in the C language, but more commonly, you'll probably be working with while loops. So with that said, we'll move on to our next example. So maybe this is your first programming language that you've used, or maybe it's your 10th, but inevitably you are going to make a mistake and create some bugs. So I want to go ahead and show you a bug in C. So let's say we have our code here, and I'm going to go ahead and just make this a little bit bigger so that you can see everything. And let's say that we do something like forget the semicolons. Now, the semicolons in the C programming language terminate a statement. So here's an example of a statement, countdown equals 10. It's very firm in what we're saying here. So we terminate it with a semicolon so that we can move on to the next line. But let's say we forgot that. So the C programming language doesn't know when we've ended our statement. So I'm going to go ahead and try to recompile this program and you'll get an error message here. And sometimes the C programming language and the compilers like GCC can be pretty good at telling you the message. It says expected a semicolon before this bracket here. So we can go ahead and just put a semicolon there, and then we'll go ahead and recompile, rerun, and our program is happy. Now, sometimes when we run into bugs, like let's say I forgot a curly brace here after main, and again, I'll try to recompile, and you'll notice I only really made one mistake, but I'm getting all these errors here because they sort of cascade from this top error, and then those bugs cause other bugs, which cause other bugs. And my warning to folks is when you see this, not to panic. Sometimes it's just a small little bug that you made. In fact, instead of seeing all these multiple bugs here, you probably only really made one that you have to fix, and oftentimes that will fix the other bugs. So if I were to debug this, I would start from here and say, okay, the main error happens around line 6 here. That's the information that it's giving me from the compiler. And I would look at this and say, okay, this looks fine, but maybe the line above or maybe the line below is causing problems. So if I look to the above here, I can see I forgot this curly brace in our main function. So now I can go ahead and rerun my program and recompile appropriately. So the lesson is don't panic and try to fix your bugs from the top. And as you're writing code, make sure that you just make small incremental changes as you're learning the language. Save often, recompile, rerun, or refix your code, and then repeat that process. So these curly braces that I've talked about in some of the lessons, well, I haven't exactly described what those are. And C is a curly brace language. So you have a left curly brace and a right curly brace, and they match in a pair. And what those define is the block scope. And that is a way to sort of divide our program into different functions, different blocks of code, like the example with the for loop or the while loop, and ultimately provide some structure to our program. So let me go ahead and show you an example of how the curly braces enforce block scope. So if I create some variable here, like x, and assign it to 42, I can safely print out x is its value, just like we learned here, and this program should work. So I'll go ahead and compile it just so you can see. Now, if x is defined in another curly brace within here, and I usually indent my code for every left curly brace that I have, and I'll try to match the right curly braces, then x's scope is just within these curly braces, which it was defined. So x's block scope is within this curly and this curly brace. So as soon as we leave this curly brace, well, we have no notion of what x is. So I'm going to go ahead and try to compile this program. I'm going to have to extend this window here so you can see the errors, and it says x undeclared because, well, we don't know about x. It's hiding between these two curly braces, or that's the scope. And the purpose of this, again, is to be efficient and to allocate resources just between these curly braces. And then as soon as we're done, our computer program, while it's running, will get rid of x. In your next lessons in C, we'll talk about how this works with something called the stack, which automatically clears your memory, or in other words, your local variables that exist between these curly braces. And that might be a familiar concept for folks who have programmed, and the same thing applies in the C programming language. So now that we know about curly braces and how they sort of separate out our program, we can start looking at how to create our other functions in C. So we've only been working with one function so far. That's the main function. Remember, that's where our program starts. But what if we want to write our own functions in the C language? Well, we'll look at that next. All right, let's go ahead and look at an example of functions. As you know, functions themselves have to be fun, and I have to make that joke. So let's go ahead and look at functions anyways, and I'll write a function here, square, and it'll take in one parameter, and it will return x times x. So let's go ahead and see how this works, and then we'll slow down a little bit to explain what exactly is going on. So I'm going to go ahead and do printf here, the square of 7, and then an end line. Well, let's say what it equals, the result. And then I'm going to call this function here, square, and pass in 7 and a semicolon. And let's go ahead and compile this program and run it. And we'll see the square of 7 is 49. 7 times 7 is 49. So there's actually quite a bit going on here. We're calling this function from within another function, printf, and we've defined our own function here. So let's try to break this apart just so we can start seeing how the C programming language works. So let's start with square here. So the basic idea is I have int here, square, and then within parentheses, another int, and then x here. So what's the anatomy here with this function here? Well, this is actually the return type. And what this is stating is that we're returning some value that's going to be an integer. Okay, so some value that's negative, say 2 billion to positive 2 billion, and a whole number or just some integer value. We have the name of the function, which we've uniquely given it. This is how we're going to call our function. So this is the name. And then we have our parameters. We could have no parameters or pretty much any number of parameters, though usually 5 or less is normal. And this specifies a temporary variable in our function. And we've just named it x. In fact, just to give it a little bit of a better name, because we're using x a lot, let's just call this arg. This is the argument. So I'll update this to be arg times arg. And you'll see it works just the same. And it's probably good to name our variables good things or have more description to them. But again, just like all of our other variables, they have a data type. So arg is always a integer value. All right, and then we of course have the body of our function. That's between the curly braces. And that's where we do our return statement. So return, and then whatever our return value is going to be, some sort of integer. So x in this example, or arg if we're looking at our code, times x. Well, multiplying two integers will give us another integer value back, so we're okay there. All right, so that's the basic anatomy of our functions in C. We have the return type, the function name, any arguments, and then the return. And then we have our body of code between each of the curly braces here. And that defines the scope, so where things are going to exist in our functions. So let's go ahead and write another function here just to make the point more clear. And in this example, I'm going to have no return type, which is also an option because we might not need to return a value. So I'm just going to call this void. The function's going to be hello. It'll take no arguments. So sometimes you'll see this empty or type in void. The curly braces. And I'm just going to use puts and say hello with an end line. And we'll go ahead and call that function, hello. And let's go ahead and recompile our program, run it, and we'll see that we get square and hello printed out here. All right, so now we can see how we can write these functions and they become a little bit more powerful. So let me go ahead and clear up a few other concepts here, because it's interesting that we were able to call this function as sort of an argument of printf, and that's allowed. This is going to be evaluated first, and then we'll fill in that value of the integer returned here, just like we've previously done with printf. But just to make that a little bit more clear, I'm going to go ahead and just create a variable here. I'll call it result, and it's equal to the square of 7, and then I'll just put in the result here. This is also legal and perhaps a cleaner way of writing our C code. So I'll recompile, rerun, and you'll see we get the same exact result. All right, and the other detail that I want to show in the C programming language is that we have to declare our functions, that is, put our actual functions before we use them. So if I take this code and I put it after our main program, and now I try to recompile this, I'm going to get a bunch of error messages here. And it's going to warn me, which, well, we haven't seen warnings yet, but warnings are as good as errors. If our tool, that is our compiler, GCC, tries to be smart, it might reorder our functions, but it's warning us and saying, hey, you're using this thing square before we know about it. Because if we look at our code here in main, we see square, but we have no idea what it is. It's way down here. Remember, our computers are pretty simple. They're just reading line by line by line, trying to figure out what's going on. So typically, we'll declare and define our functions before we use them. Now, there is a way to get around this that you might see in some C code, where I provide the function declaration and put a semicolon to say, hey, this exists, and this matches the exact return type, the parameters, and the name, which I should match exactly here with arg. And then that tells my compiler or GCC that, hey, this square will eventually show up. So I'll need to do the same thing for our hello function. And then I can recompile, and no problems here. And let me go ahead and just show this all on the screen at once so you can see what happens. And again, we can declare that our functions exist. Now we can use our functions. And here's the definitions of our functions. And again, a definition means that you're defining how you actually do the work. Here's what you're returning, or here's what you're printing out with your hello world. So there's all the code for you to take a moment to look at, and we'll go ahead and move on to our next example. All right, if you've done programming in other languages, you maybe have heard of the concept of recursion. And C, like other languages, allows you to recurse and call a function from itself. That's a little bit confusing, so let's go ahead and show an example. If this is your first time with recursion, don't worry. We could look at many other examples at a later time, or you can look at some web resources. But I want to go ahead and show you that it's possible in C. So I'm going to go ahead and write the countdown function that we previously looked at, and it's going to take n, which is the value at which it counts down. And in order to write a recursive function, we need to have our sort of base case or the terminating case. And for that, I'm going to say if n is less than 0, then we will return. Otherwise, if that's not the case, or otherwise I can just return by calling the same function again with a value of n minus 1. So n is always shrinking here. And then I'll go ahead and print off the string here for whatever the value of n is. %d, and then n that's passed in here. So let me go ahead and make this a little bit smaller so we can see all of our code. And I'll call our countdown function with a value like 10. We'll recompile and rerun here, and we can see our countdown working. So here's all the code as it is. So let's go ahead and slow down just a little bit with recursion. And the idea is in our countdown function, and let me go ahead and label it here, countdown, I need to have some sort of base case, and that's sort of the smallest value or when things terminate. So it can be the base case or the terminating case. And then I have the recursive step. How am I making this problem smaller? Or how am I approaching my goal? Well, in the case of our countdown, we're shrinking every time. So that's the goal, the recursive step where we shrink or approach our base case. Now, this isn't necessarily a lesson in algorithms, nor is that the purpose, but I just want to show you that recursion is possible. And then we're going to continue a little bit further with this example, just to show you how to write some better C code in the next lesson. All right, so there is a way that we can go ahead and improve this example. Because what might happen is, what if a user tries to count down from -10? Well, if we're shrinking every time, what happens? Well, let's go ahead and run this code. And, well, it doesn't really do anything because we just return here. So we might want to add some safety to this function. So we can do something like make the value unsigned. So that means that one of our primitive types here, we can qualify and state that it must be a positive value. That is without a sign, no negative in front of the value. So I can go ahead and try to run this, and it'll give me some sort of positive number, and it'll probably crash though, because, well, I still passed in -10 here. So what can we do to sort of enforce writing good code? Well, the C language many folks say is dangerous, but there's ways that we can be sort of safe programmers. So what I'm going to go ahead and do is include something known as an assert, assert.h, and in my actual function here, I'm going to write what's known as an assertion statement. So how do I do that? I write assert, and I say n must be greater than or equal to 0, and I can put in 2 and signs to give me a warning and say n was not greater than 0. So this asserts every time in my code that n, or any time this function was called, must be greater than or equal to 0. Otherwise, it's just going to crash the program. So we won't get that sort of unpredictable result here when we have -10. That's not allowed to happen when our program is running, or in other words, during runtime. Let's go ahead and compile, and I'll try to run. But strangely, when I run this, it's still sort of crashed because of how C, again, sort of treats these unsigned numbers. So what I can do, or what my recommendation is when first starting off with C, is just use an integer, then use this assert here, and we'll go ahead and try to run it. So in case users do provide a negative value, we can try our code, and we'll get the assertion message with the warning here telling us that, well, we provided a negative value. So by default, on your first day in C, just rely on simple types like integers, and you can write little assert statements to help make sure that your code is safe. All right, so with this lesson, we've now branched out a little bit to understand that there's more different libraries in the C programming language that we can take advantage of. Pretty cool, huh? All right, let's go ahead and continue on forward. So with some of our countdown examples that we've had previously, we've seen the if statement pop up. So it's time to now talk about if, elseif, and else statements. So let's go ahead and rewind with a little simple example, creating first an integer and setting it to some value here. Now in C, we have if, and then we can do conditional statements. I could say if this is greater than or equal to 0, and x is less than 50, then go ahead and print off x is in our range. And this is perfectly valid to do. So let's go ahead and run this code just to show that it compiles. Again, working from simple examples and building up, and we can see that's in our range. And we can also, instead of using and, use a Boolean operator to say if x is greater than or equal to 0, or x is less than 50, which it satisfies both of those conditions, but as long as it satisfies one, we're okay. So let's go ahead and run this. X is in our range. Let's go ahead and just set it to -42 to see that one of these conditions is true. And again, x is in our range, prints out. Now, let's say that we want to do something with else conditions. So we could say if x is greater than 0, we'd say x is positive, and it's a positive integer. Otherwise, we would say, and I'll just print off, x is either 0 or negative. And let's go ahead and run this to see what our result is. And x is positive here. And if I go ahead and change this program, and I'll resave, that means I need to recompile, rerun, then x is either 0 or negative. So this is our if and then else condition. So if this is not true, then execute this block of code. And then in C, we also have else if conditions. So we could say if, and it'll evaluate this condition first. else if x equals 0, then we could print off x is 0, and I'll put an end line there. Otherwise, if it's neither greater than 0, if it's not 0, then it must be negative here. And I'll go ahead and update our text here. So we can go ahead and rerun this example and see what the value is. All right, now me having to constantly recompile every time I change this value was a little bit annoying. So in the next lesson, we'll learn about how to get input in from the user in our programs. All right, so let's go ahead and modify this program a little bit so I can determine what the value of x is from the user. So what I'm going to go ahead and do is just assign x to 0 here. And then we're going to put out a message here. So I'll put out a string, enter a number for x, colon, and a semicolon. And then a new function called scanf. So scan formatted text. Well, what kind of text are we reading in? Well, it's an integer, so %d. And then I'll close it off, and then we're going to use ampersand x, because this is the value that we're going to be changing. Now, why the ampersand? Well, that's going to come in the next lesson. Just bear with me for a moment why we have that ampersand. So what we're going to go ahead and do is run gcc. We see that our program compiles. I'll run it and it says enter a number for x. Let's try 42. X is positive. And now I'll rerun that program. I'll put in 0, x is 0. I'll rerun it again, -50, and x is negative. So scanf is a way for us to read in formatted data. If this was a float, I could put %f, and as long as x was a float, this would also work. So that's the idea here. Now, where does this ampersand come from? This is one of the mysteries of C, but also one of the reasons why we like the language. It lets us see some low-level details, which we'll get into in the next lesson. All right, let's go ahead in this lesson and revisit this idea of ampersand. And I'm going to go ahead and just clear up some of this terminal here and give us a fresh start here. So to understand what the ampersand's doing, let's go ahead and just create a variable. X, and we should always initialize our variables, so I'll set it to 42 here. So visually, what I have here is some name location X in my computer. So I'm just going to draw a box here, and it's labeled X. And stored inside of this box is the value of 42. So anytime I use this variable X in my program, it's just going to look up the value in the box and send it to us. But where does this box actually live? And you could sort of imagine this like an actual mailbox on your house here. And I'll try my best to draw this actual mailbox here. And maybe you have a flag here if you have mail. At least this is how our mailboxes work in the States here. And if I want to see what the actual address is here, you know, your street name and the location, you know, 1, 2, 3, or whatever it is, how would I get that address of this box? So what that is the ampersand gives us. This is the ampersand operator, which will return to us the actual address of this mailbox, or where we live, in other words. So we can think of ampersand again as a function. So I'll go ahead and show it to you in how it works here. So let's go ahead and just do printf. And what I'm going to do is print out some number here. And I'm not going to print out 42, but I'm going to print out the address of X here. And let's go ahead and see what this gives us in our program if we recompile. It says, this expects an integer, but the argument has a return type int star. Okay, this is a little bit strange here. If I try to run this, it's just going to give us garbage, some negative value here. So what I really need to do is pass in another format specifier, %p. And this is going to lead us into our next topic here. But now it compiles without any problem. And if I run this, you'll notice I get some address here. And you'll notice that there's a 0x here, and then some number here, 7FFD65834704, etc. Now your number might be different because we have different computers, and my computer is storing X in a different location. That's fine. But this here is the address of where X lives. So this mailbox here, and it stores inside of it 42. Now, how would we get from this address what's inside of the mailbox? Well, for that, there's actually something cool. So this statement prints out the address. That's what %p format specifier gives us. If we want the value in the address of X, and you can think of it as %x or ampersand with the parentheses around it, we can instead use this asterisk that popped up. So this says, give me the address of X, and this asterisk out here, it doesn't mean multiply, but rather what it means instead is look inside of this box, and from this reference or this memory location, give me the actual value. So let's go ahead and run this. And again, we'll see the warning here because the specifier is not right, because what is X? Well, it's an integer. So let's go ahead and make sure in our format specifier, we pass in %d. I'll go ahead and run this, no warnings, and just sort of like magic, we'll see we get the value 42. Now, this is where we need to talk a little bit about another topic in C programming, which is known as a pointer. So let's go ahead and dive into that in the next lesson. So in this lesson, I want to talk about a fun concept known as pointers. They're really powerful in the C programming language, and one reason why we use it. They give us this low-level access. So what exactly is a pointer, though? Well, a pointer points to something. That's one way to think of it. Or the other way is just that a pointer stores a memory address. And we've just learned how to get addresses with ampersand. Okay, so let's try to connect these ideas by looking at a few short examples. And remember, this is your first day in C, so we just want to try these and try to wrap our head around it just a little bit. We'll internalize or understand the point of pointers a little bit later on as you get some more practice in your C career. But let's just start off with the basics. So again, let's just create some variable x equals 42 here. And we've learned how to get the address of x here. So let me go ahead and print out that address using %p. So the address of x is, and we do that by using the ampersand x. And again, if you want to think of ampersand as a function, I'm going to go ahead and wrap this and pretend x takes in an argument. That's also fine. Close or balance our parentheses and semicolon. So let's just go ahead and start with this much here, recompiling and rerunning our program. And this will probably look a little bit nicer with an end line. So let's go ahead and run this here. And we'll see the address of x is, well, what I've displayed here. Again, it might be different on your machine. Okay, so if a pointer here can store a memory address, how does that work? Well, first let's declare a pointer. Declare a variable that is a pointer. Okay, so what does this mean is I'm going to have some variable here, and I'm going to call it p of x, and its job is going to be to store some memory address. So something that's 0x, f, whatever the address is. All right, so how do I declare a variable? Well, to do this, there's a special syntax, int star or int asterisk. And this is a pointer type. You can think of the star as a point, but it sort of belongs to the integer here. And I call this p of x. And since it stores an address, well, I need the address of something. Let's just store the address of x. And let's go ahead and print it off. So I'm essentially just going to copy this line here, and let's paint it here, or paste it right there. And I say p of x is, and let's just go ahead and print out the value of p of x. And if p of x here, px, stores an address, well, I use %p to print out address values. Let's go ahead and just compile this code. And if I run it, you'll see the address of x is 0x7ff, etc. And we have a matching address stored in p of x. So pointers store addresses. and I can point to other variables. So essentially what I've done here is I have this other box x here, which stores some value, 42, and p of x stores, well, whatever this box is. Now I'm not going to draw into the box, but it just knows the location here, 0xff, whatever. And if I want to get the value inside of the box, I have to dereference, and that's where that asterisk came in here. So this was creating a pointer, and this is accessing the value to the thing we point to. So let's go ahead and do that. And I'll do that just with a printf here. And star p of x value, or the thing we point to, the value of the thing we point to is, and this is specifically an integer pointer. We can point to other integers like x, which is an integer. We could create a float star, which would be a floating pointer. It could float to or point to other things that are floats, and the type matters, or even if we have custom data types, which we will reveal shortly. So that's the idea here. So %d, that's the thing that we're storing, and we're dereferencing, so the star p of x. And again, I can think of this as a function, the asterisk, and it goes before the variable, just like the ampersand went before the variable that we were trying to get the address of. So let's go ahead and reveal that it compiles and it runs. So we say star p of x, the thing we point to, the value is 42. Now, this is pretty cool, and you might be wondering what the point is. And I'll end the video showing how we can build data structures with this. But allow me to just give you a little bit of a teaser here. If I created a second pointer here, and I'm just going to call this px2, and it also points to the ampersand x. Now, let me just go ahead and create all of these variables at the start of my program here. And p of x2, which I'll draw in our picture here, and let's go ahead and label it appropriately, px2, also stores some address. But if we're pointing to this same box here, that means we're effectively sharing the value. So pointers are a way of letting us share data by just pointing to one consistent location. It's sort of like if my information was in a database and a bank sort of points to my information and some company or cell phone provider points to my information and my employer points to that same information. We'd want it to be the same. So that's sort of the idea here. So anyway, let's go ahead and just print off. If I put asterisk px2 here, or in other words, dereferencing, then let's see that we get the same value here. So if I recompile, rerun, p of x when I dereference it is 42, and px2 is also 42. So try typing this out, try drawing this out, and then you'll sort of get the point of pointers. We store addresses, and when we use equals, we assign or point to things. Again, it's your first day in C, so you might not 100% get it, but understand that it's a very powerful programming concept. So we've just learned about pointers, that they point to memory locations. And we've learned about some other things like arrays. And I want to motivate a little bit more why pointers are powerful or a cool thing with something that we've learned previously, arrays. This idea that I can allocate, say, 5 items together. Remember, we had this piece of code here, int array, and we said 5. So this array was always going to be 5 elements large, right? And we 0 index 0, 1, 2, 3, 4, and we put in some values here, 23, 76, 0, etc., etc. I'll just make up some numbers here. All integer values stored contiguously in this block. But what if I don't know what this size is going to be? Should it be 5? Should it be 10? Should it be 1,000? Or maybe the user should decide. Or maybe you're loading some data from the internet, and however big that data set is, that'll be the actual size that you need. So in other words, how many boxes we need, we can't always determine before we save, compile, and rerun our program. So this is where we bring in two functions known as Malloc and free. And they have to do with dynamic memory allocation. And we use a pointer to help us with this. So in other words, Malloc means memory allocator, and free means, well, freeing that memory, essentially just getting rid of this storage that we've requested so that our machines can use that memory for something else. So let's go ahead and look at an example here. Now for this, I'll need to include a new library, std, which stands for the standard library, and then .h. Okay, so let's go ahead and see how we use this. So I'm going to need to create a pointer, and I'm going to call this dynamic array. And it's going to be equal to, well, Malloc. And this is the memory allocator. Think about this as some program, if you like, in your operating system that hands you out memory when you ask. And it will hand you out as many bytes as you need. So how many bytes do I need? 4, 8, 12? It's up to you. That's what the parameter is, 112. But there's a little bit more of a disciplined way to handle this. You can use size of, and then how big the data type is. So an integer, and this function will return you the size of an integer, which is usually 4 bytes. Then how many of those do you want? Do we want 100? Maybe just 5 for this example. Let's go ahead and run with that. So that's the Malloc function. Now I'll go ahead and compile this program, and I'll run it, and no problem. Well, almost no problem here. I've asked for this memory while our program's running, but I never released it when I was done. And that's the polite thing to do. We need to, before our program quits, free this memory. So we use this function here, free, and we free our dynamic array. So then we are done with our program, and it's executed successfully. And we use this dynamic array here because we've allocated 5 integers in a contiguous block again, and we're pointing to them here. So we can just use our arrays as we did previously. Here's the first element, and we'll assign it to 23. And let's go ahead and do all 5 of our elements that we use just as a normal array here. So let's do 76, 0, 5, and 81. So it matches our diagram. All right, so nothing really new there in the sense of we've learned what happens, except this is again the point of a pointer here. That's called dynamic array. So I'm going to go ahead and get rid of this and label our dynamic array here, the variable that we created, and that's a pointer. So it points to things. So when I assign it equal to Malloc, this gave us 5 boxes of memory. So I'm going to weave my arrow around here and point to the first chunk of that memory. And then the assignment here, 0, 1, 2, are the little offsets into each of the boxes here. I'll offset by 0 from this initial chunk here, offset to 1, offset to 2, offset to 3, offset to 4, etc. as I access each of the elements in this array. And this is what's known as a dynamically allocated array here. We assign it with a pointer, ask for some memory while our program is running, and then we assign values just like we normally do with arrays, and then free that memory when we're done with it. So that's also one of the points of pointers. It allows us to do this at runtime where we can ask for the size here. Now, again, just to show how this is a little bit more dynamic, let's go ahead and create a variable called size of array, and I'll assign it to 0 by default. We'll use one of our functions we've learned about before, scanf, %d, because we're reading in a integer value, and we're passing in the size of the array because this is the address of where this box lives. And we use an ampersand, which I'll have to talk about with functions momentarily. And now I can dynamically size this array by just passing in this parameter here. So then when our program runs one line at a time, setting up the size of the array, reading in that value from a user, and then allocating while the program runs the appropriate amount of space or the number of boxes that we need, and then we can fill them in using, say, a loop here. And let's go ahead and do that. For int I equals 0, while I is less than, well, however big our array is that we asked for, we'll increment and just set up each of the elements in our array at index I equal to, well, just 0 for now is fine. So let's go ahead and run this program just to show that it runs. Doesn't really do anything useful. I've got to add how many elements I want to allocate, 99, and then it will set each of those 99 elements to 0, and then free the array and exit our program. Anyways, I hope this gives you a little bit more intuition. In fact, this is sort of our second data structure. We have just regular statically allocated arrays, which we fix the size, or fixed size arrays, and this new dynamically allocated array. So let's revisit this example, or at least one part of this example briefly. Why am I passing in ampersand size of array here? Why does the ampersand have to go in here and not just the variable name? Well, I can give you a quick answer by just closing out this code and showing you one of the useful resources in C here. And that's the help pages. So we can sort of just guide ourselves. I can type in man, which is short for manual, and scanf. And on the terminal, it'll actually show me the pages. Now you can also just Google this command and you'll get some help as well. But it tells me what library I need to include. That's why we've been including standard IO, and then the particular function we have. And then the parameters are, well, how we're going to format things. So that was the %d. And then I just see ... Now, this probably isn't the greatest function to start from, but the idea is you eventually need to pass in some variable here, and the address of that variable is what's getting filled with some data. So let's go ahead and look at writing an example here of how to, or what happens with this ampersand size of array here. So I'm going to go ahead and clear up this code here and write a function here. And it's going to be called set value. And I'm going to set a integer value here. Now, first, let me just try it with int and then new value. And I'll go ahead and set new value equal to 9999 here. And we'll go ahead and see what happens here. So we'll create int x, set it equal to 42. I'll call set value. I'll pass in x. And then I'll go ahead and print out x is, and then whatever the value is here. So go ahead and pause and take some predictions as to what is going on here. So I'll recompile the code and it compiles, and in 3 seconds, I'll run it. 3, 2, 1. Did you make your prediction? X is still 42. All right, so what happened here? So C has something called pass by value. So pass by value. And what this means is we make copies of variables when we pass them into functions. So pass by value here. So essentially what this means is when I call the set value function here, set value, and its first parameter is new value, and if I call it with x here, I get a copy of x here. I don't get the actual x that we set up at line 42, but instead a new copy is made. That new copy of x is set to 9999, and then that copy goes out of scope when we leave these brackets here. Because again, the C language is trying to be efficient. Now, if I want to change this value, because remember our goal was to do something like with scanf, where we were passing in some format to tell us what kind of value we're working with, and then ampersand some value. So how do I pass in an address to a function? Go ahead and take a moment to think about that. And if you thought about it for just a moment, well, what stores addresses? Well, pointers. So I need to put int star. That's the type here that I have. And now I need to, well, pass in the address of something. So if I pass the address of x, that's giving me the actual address of where x lives. So that actual location now is what's going to be changed here. But we're not quite done here because, well, how do I access the actual value? Well, in order to do that, I need to dereference. So I'll use the star here, and I'll put parentheses just to be clear. And now, if I run this program, what's going to happen? And make your predictions in 3, 2, and 1. And you'll see that x, after this function has been called, since we're passing in the actual address of x, does in fact get changed. So this is why in some functions like scanf, where you see an address being passed in, that's because we actually want to change that actual variable. And that's known as pass by value semantics. All right, so you're going to see that a lot in the C library, for example. And we'll go ahead and move on to our next example. So now that we've talked about pointers, pass by value, arrays, and some of these concepts, I want to start putting some things together. And one of the things that we have been missing is strings. We have been using strings in the sense of, well, whenever I call one of these functions like put s or put string, between the quotation marks, I have a string here. So instead, what I want to do is actually show you how to write a string literal and how we represent that. So we use one of the primitive types here, char, for a single character. And a single character would just be something like this here. And I can try to print this out here. Let's just see if it'll actually print this out here. And it's actually going to complain here. And if I look at the function signature for put s here, which I'll go ahead and split this window, look in our manual page, which you'll get in the habit of, we'll see that the put function, if I look at it, for put string, takes this thing called const char star s. So what does this exactly mean here that our strings are taking it? Well, let me go ahead and close this. And again, any time that I have some pointer here, so I declare that with char star, that means I'm pointing to the first character, because that's the type here. And again, this is pointing, that's what the star means, in a chunk of, well, however big our array is. So let's first look at this with a string literal. And a literal means just a literal string here. So it could be something like hello. So let's go ahead and try this out. So instead of just storing one character, I want a block of memory here. I'm going to point to some chunk of memory here. And with 2 quotation marks, not just the single quotes, this will make a string here, and I'll put hello. And now I'll try to recompile, and I'll rerun this program, and I'll get hello. So that's the idea of a string literal. Now, since this is a literal string stored in memory, and it looks like I have an array here, so 0, 1, 2, etc., can I actually access each of those individual characters, and how would I do so? Well, what if I did printf, and I said, well, in this array, which I've named a here, a of 0, let's go ahead and try to print this off. And this would be an individual character, so %c, a of 0. And I'll go ahead and compile this, and, well, I get h here. And I'll go ahead and put an end line here just to make it a little bit easier for you to follow along with. If I rerun it, there we can see it is. Now, what if I want to actually change a of 0 and say it equals now b? And let's go ahead and just do this before we print it off to see if the change is reflected. And I compile it, and this time I get something called a segmentation fault. So it looks like I can't just change the string literal here, because this is sort of a constant value. So there's actually a different way to do this in C, where I'll get rid of the star here, and I'll put the brackets after the A. And C is smart enough to figure out that this array of characters is going to be 1, 2, 3, 4, 5 characters. Or there's actually a 6th character, but I'll get to that in a moment. So let's go ahead and just try to run our program again, rerun it, and this time it works. So there is a difference. There is a difference between char star A and, I'll put on a separate line here, char A with the array here. This is, again, a string literal that says this is a literal string. You cannot change it because it is literally just hello somewhere represented in memory. Versus this, which is an array. And arrays are pretty flexible. We can index into them, we can change the values, and so on. So remember the brackets with array. And for strings, remember the special case where you have a char star and can't change it. Now, getting to the length of this. Well, when I'm printing off this array here, and in fact, let's do this looking at put s for the string, how does it know where to stop? How does it actually know that it's not hello Bob or hello Mike or hello whoever? Well, in fact, what C does automatically for us is it puts a terminating character, and this is called a null terminator with a backslash and a 0. That's a null character that says end this string. So it's as simple as that. 1, 2, 3, 4, 5, and then this backslash and a 0 is the 6th character. So that's how C knows how to terminate strings. And if we want to go ahead and see this, we can use a handy function here called strlen, and it takes in some sort of string here, and it'll return the size here. So it says the strlen function calculates the length of the string pointed to by the s, excluding the terminating null byte here. So it should give us 5 characters here. And in order to use this function, we'll include string.h here. So let's go ahead and do that. Include string.h. And let's go ahead and just print off the length of our string here. So I'll do it here. Print off length of string A is, and we'll put %d here. And call the strlen function on our string A. And let's go ahead and see what we have here. Now this is saying here that we're getting a warning here. So let's go ahead and look just a little bit closely at that function here. And the warning is fine. It'll probably still run, but we want to take care of warnings in our C code. So the manual page strlen, and this is going to tell us that it's returning a type size_t, which is actually a sort of positive long integer. So it's telling us that %LD is the correct specifier for the value that's returned here. So let's go ahead and amend that and follow the recommendation of the compiler here. And if I go ahead and rerun this code and run it, again, we'll see the length of the string is 5. But we will want to be careful here because the length of our string is actually 5 characters plus this null terminating byte. Because again, the C language and the functions where we pass strings into have to know where to terminate the string. And that's the null terminating character. All right, folks. So then we'll do one more lesson and then we will wrap things up with a little data structure that I promised way in the beginning. So looking at some of our previous examples, it's been cool that we have strings, floats, string literals, we can point to data, but what if we want more complicated data types beyond just our primitive data types that we've had previously? Well, one way is that we can compose primitive data types or other custom data types that we've made into a structure. And that's exactly what a struct is in C. So I'm going to go ahead and just remove this here and show you how to create a struct. So a struct here is some way to, again, structure data together. And I'm just going to call this student here and then put a semicolon here and some attributes of a student. So again, you could think of this like an index card with all their information. Maybe their age, maybe their ID, maybe their average grade, which we'll just store as a character. And if we wanted, we could have maybe some array storing their name. Let's just go ahead and leave that as is. Okay, So if I want to create a student, I type out struct student, and I'll use myself as an example, Mike. And then I can index into each of the fields by saying Mike age equals 500. And then let's go ahead and just print off Mike.age, and this is an integer, and I'll do an end line, Mike.age. And let's go ahead and run this much of our program and see what happens. So we can see Mike.age here. All right, and let's go ahead and add the rest of our fields. So I have my ID, which will also be 1, 2, 3. And I'll have my average grade, which, come on, folks, A, of course. So let's go ahead and print these off. ID. If I'm being realistic, it was probably a B average. So let's go ahead and leave it as is. Average grade here and ID. So if I run this here, oops, looks like I missed one error here. Again, let's look at our error message before I just go ahead and fix it. But again, always starting from the top because we see this error here. We'll go up here, look around, and find that we need to close that right parentheses. Now recompile, rerun this, and we'll see our printout here, which I can improve it and add some spaces and these kind of things here. Sometimes I like to align things nicely here. Let's go ahead and do that for this example, just since we're getting close to the wrap up here of this lesson here. But just to visually sort of show what's going on is when I create this student Mike, which again is a structure, what I have is these 3 fields that belong together. Again, the age, the ID, and then the average grade here. And this is what makes up Mike here. So that data is sort of packed together and travels together. It's structured together. And we could pass in this struct Mike into functions, for instance. There is one nice cleanup thing that we can do here. Instead of having to type out struct and then student every time, we can actually in C use type def. And then at the end here, we would just say student underscore T. So instead, and I'm just going to comment this out here, we can just say student underscore T and then Mike. So that'll save us a little bit of typing in our programs, and you might see both in C here. So I'll recompile it and rerun it. Now, let's go ahead and instead of having to print this off here, let's just call a function where we pass in our structure. So I'm just going to call this print student, and it'll take in a student T. And again, I've declared my structure above my function, so I can use this here. And I'm just going to label them S. And let's go ahead and take our printf statements. I'll pass them in here. And we don't want these all to be Mike here. Let's not assume anything. There are a lot of Mikes in the world. But let's just make this S, S, and so on. And then we'll just call our function print student, and I'll pass in Mike here. So this will make, again, a copy of Mike. So a copy of these 3 fields and pass them in here. So let's go ahead and compile that and run it. And we can see our student, again, that's being printed off, that we've passed in here is Mike. So that's our structured data. Now, all the things that we've learned before, we could also have a pointer here. So let's go ahead and create a pointer. So student star here. And let's go ahead and just try to compile this. And let's go ahead and see what happens here. Let me go ahead and change my layout here. So I'll recompile. And all sorts of errors, all sorts of madness here. So where do we start, or where did things go wrong? Well, first off, we need to be passing in the address here. So let's go ahead and try to fix that here. So I'll pass in the address, Mike here, because remember, pointers store addresses. And I'll recompile this, and fewer errors, so that looks better. But now the compiler is saying S is a pointer. Did you mean to use arrow? Okay, what's arrow? That's something new here. So let's go ahead and just follow the compiler's recommendation here and see if that works here. S arrow, SID, S with an arrow, and the average grade here. And wow, it compiled. And now if I run it, it's doing the same thing that it did before. That's amazing. So we get our values here. Okay, but what is the arrow actually doing? Well, the arrow is doing a combination of dereferencing and accessing a field. So another way to write this is I'm still accessing a field with a dot, but I'm actually dereferencing that specific field. So I'll put it in parentheses, and let me just separate it out a little bit here. So if I recompile this, oops, let me do this properly. Then we can actually see what's going on here. Now, you're going to notice I got errors here because we need to do the correct order of operations. So I need to dereference first, that is, follow my pointer to find the actual value, the actual student, Mike, somewhere in memory, and then access the ID. So if I compile and run, this time it'll work. So just take a moment to observe that this sh with the arrow here is doing this exact same thing here as ID. I'm dereferencing S to figure out who the actual student is, and then dot accesses a specific field and gives me the ID. So I'll go ahead and just, again, draw this out. So if I have Mike, and then I do a dot, that is selecting whatever the field is from my structure here. So dot age. And when this was a pointer, I have to first, well, since I'm pointing to something, right, I just have some random pointer here. I need to find my student, however I point to it, dereference it so that I can look inside of the boxes, and then access the specific field with a dot here. So then I did the star around Mike to, again, trace around and find the box that I need, and then the dot to select the appropriate field, whichever field that might be. All right, so that's the idea of structs to structure our data together, and we can use them with pointers as previously done. And just like our other concepts that we've learned where we've used data types, we can create, and I'll refactor this a little bit here, as many students as we want. So I can call this my classroom, and I can have 500 students, and student 0 has an age that we can assign, and so on. And if we want to, we can do this dynamically if we don't know exactly how many students we'll have. So I can make this a pointer, and I can set this equal to, well, the size of however big our student T data structure is. And then if I want, say, 700 students this time. And let me go ahead and make sure this compiles. And since I'm using Malloc, I need to include the standard library. That's what this error is giving me. And our compiler is pretty good about giving us errors here. At some point, they're just going to write the code for us, right? So let me go ahead and recompile that. And we say, oh, error for conflicting type here. Okay. What exactly happened here? Well, I just spelled student wrong. So let me make sure I recompile that. And it still says error for conflicting type. And, well, I can't name things the same thing. So this is our dynamically sized classroom here. I'll recompile again. And, well, should I run it? Is it bug-free or not? And maybe some of you who remember will also have to free our dynamic class before our program ends here. So now I can recompile it and rerun it. All right, so now you understand or have an idea that structs exist, and we can create our own custom data types. All right, so our grand finale and coding examples before we wrap up is to show you a new data structure. And this is going to be known as a linked list. Or I'm at least going to give you a partial implementation. And the idea is we're going to create some sort of struct here that's a node. It's going to have two fields in it. One is going to be some data, which is going to be an integer. And the next field is going to be a pointer to some other node. And that will point to the next node in our linked list, which will store another node with an integer and another node, t. And this will continue on to another node somewhere in memory here, int node t, until we reach a value in C known as null. And this is exactly similar to the null terminating character that we saw with strings earlier, except this time we have structures and we're just going to use this null type to indicate that our pointer points to nothing. That's how we use null in C for our pointers. So let's go ahead and create the structure. So I'm going to use type def again. This is a struct node, and then node t is how we'll declare it. Now, of course, you can use struct node, but node t is a little bit shorter. The data that's carried in each node is an integer, and I'm just going to call it the data. And within our node, we have a node t. Now, I'm going to actually write this as node, and it's a pointer. And usually how we label this is just the next thing that we point to. All right, so let's go ahead and just create some nodes here. Node t1, and node t2, and node t3. Now, we need to access each of the fields here. So 1's data is going to equal 1, 2's data is going to equal 2, and 3's data is going to equal 3. So I'm just populating these nodes so far here. So I have 1 here, I have 2, and I have 3. And now I need to link them together. So that's setting the next field of each of these nodes. And I'll do these sort of consecutively. So 1's next node, well, what exactly is it going to point to? Well, it's going to equal, and it needs to store an address here because this is a pointer. So the address of 2. And likewise, 2's next node needs to store the address of 3. And 3's next node that it needs to point to is, well, there's nothing, so null here. So it doesn't point to anything. So this is our linked data structure. And it's really our third sort of data structure we've learned about, right? We've learned about arrays that are fixed in size. We've learned about dynamic arrays, and now linked data structures. And I'm just showing you a list, but we could have all sorts of connections with our nodes to make them graphs, or they could have cycles or multiple chains and multiple directions or self-edges and all sorts of interesting things that you'll learn about in your C journey, which is pretty cool. And well, ultimately, if we can represent something as a graph or in this structure, we can work with it in computer science, which is super, super exciting. So let's get to the point here and just try to print out this actual linked list. So how would I do this? Well, I might need some sort of while loop here, and maybe I can just have a node sort of as a temporary iterator here. And what it's going to do here is point to the first node in our chain. So it needs the address here. And it's going to say, while whatever our iterator node is, and while the next field, dot next or arrow next, is not equal to null, well, then we have more information to print off. So let's just go ahead and print off whatever our iterator is, which points to 1 here. And I'll walk through this again slowly. And let's just go ahead and say data %d, and we need to access the data of our iterator, whatever it points to. And then iter equals iter next. Okay, that's a little bit weird. Let's go ahead and try to compile it though, see if we made any mistakes. No mistakes, that's good. And if I run it, I see data 1, data 2, no data 3 though. Looks like I was off by 1 here. So we just want to look at when our iterator is not equal to null. Let me try that again, rerun it. And now I see all of our data 1, 2, and 3 in this list. All right, let's go ahead and walk through this portion here. Looping through a linked data structure. And the idea here is that I just created some temporary node here, iter, and I pointed it to the start of our chain here. Again, just pointing to this box here. And again, it's just a pointer here to other things that are nodes. And well, it needs to store the address. So again, the address of wherever this node lives here. And then I said, okay, this iterator, it's not null. It points to something, right? This actual box here. So if it points to this, and if I dereference it, which is what the arrow is doing, remember arrow means dereference. So look inside these boxes. And then if I choose the field with data, that gives me this inside data here and print off 1 and so forth. And then this line's a little bit weird. Iter equals iter next, but I'm basically saying, well, now set this iterator here to look at the thing that I'm pointing to, and inside of this box, grab whatever this node is and point me to this box next. And then I repeat the steps here where I access the data inside, and then I access whatever the next node is, and then sort of follow this chain forward here. And then I do this one more time until I eventually reach null, which is this condition, iter not equal to null. So eventually we will point to null, and that's when we know to terminate here. All right, and that's a little teaser of the types of data structures that you can build in C. And that's all you really need. Arrays, where you can decide if you want your memory to be contiguous, or this more flexible link structure where you can add things to your chain or in between your chain or in multiple directions if you want some sort of graph structure. So folks, I hope you enjoyed this crash course of C programming in a day. Now there's a few topics that we haven't touched on, things like unions, function pointers, bit shifting, and a lot of the standard C library, things like different string functions, handling arguments, and all these other different things that you can do in C. Remember, C is a language that's been used to program games, operating systems, any type of application. So there's a lot built in and there's a lot more to learn. That said, that'll leave you with plenty of fun later on to learn from. So go ahead and review this video. If you did watch the whole video, comment below, and I'm going to give you a big thumbs up for doing that. And I know there's definitely some of you who went through and did all the exercises and played around with the code, and that's awesome. So I hope you learned a lot from this video. I hope you're going to look at some of the topics that I mentioned, things like function pointers, arrays, building your own data structures, bit shifting unions, and so much more after completing this and after you've mastered some of this material. So folks, I hope you enjoyed this. Make sure you like, make sure you subscribe, and we're going to see you in the next video. And comment below if there's something else you want to see done in C. Take care.